Hi, welcome to April 1st's lecture. Today we are covering 7.6 geometric applications of radicals. I am recording this 2 days early. As I have already been doing, I am trying to post the videos in advance of when I would have been lecturing to give you some extra flexibility. I know that this time is going to be challenging for all of us, and it has gotten increasingly challenging now that Health Mandate 11 has compelled me to work at home. I am lecturing on a very small whiteboard here at my house, so hopefully I'll have minimal disruptions, but it won't be necessarily as seamless as the lectures from the college. Nevertheless, I'm going to press on. This is going to be a good lecture. I'm optimistic about that. Okay, so here we go. 7.6 geometric applications of radicals. We're going to start with the Pythagorean theorem. The Pythagorean theorem is a simple one to remember. A squared plus b squared is equal to c squared. What do these letters represent? These letters represent sides of a triangle. Not just any triangle, a right triangle. The requirement for using the Pythagorean theorem is a right triangle. That is very important. The side lengths are a and b. These are referred to as the leg of the right triangle. It's an arbitrary choice as to which one is a and which one is b. However, it is very important that you always make the hypotenuse c. Okay, so now we're going to look at number 16 from the book. This is from page 647, number 16. Here in number 16, we have two side lengths. We have the side lengths for A and B. In the book, it shows that A and B are the legs, and C is the hypotenuse, just as in the previous drawing, the previous diagram I had on the board. So what we want to do is go ahead and replicate that diagram. We label the legs 5 inches and 12 inches, and now we are going to plug in A and B to the Pythagorean theorem. A squared plus b squared is equal to c squared. Then 5 squared is 25. 12 squared is 144. And when you add 25 and 144 together, you get 169. Now here, if you want to solve this equation, what we need to do is take the square root of both sides. So we take the square root of both sides. Typically, when you take the square root of both sides, you're going to have a plus and a minus, okay? So when you're using the square root property in general, you have a plus and a minus. However, in this scenario, C represents a side length, and a side length can never be negative. So the square root of 169 is 13. And to put this in context, we need units. So the hypotenuse, C, the missing side, is 13 inches. Okay, so that's a basic example. Now I'll go to a slightly harder one. Okay, so questions 3 and 4 from the MyOpenMath problem have a similar setup. You're given a right triangle. In question 3, they don't include the right triangle box as they should have. That's a flaw of the original problem. But you can go ahead and assume on MyOpenMath, when they're giving you the triangle and they're asking you to solve for an unknown side length. You can't solve it unless it is a right triangle. So go ahead and assume that you have right triangles, even if they forget to put the box there. Anyway, question 3 and question 4 are very similar on MyOpenMath. The only difference is that question 3 wants you to round the answer to the nearest tenth, whereas in question 4 you're to give an exact answer. So let me first just walk you through how to get to x, and then we'll look at the exact answer versus the nearest tenth. So here we have the Pythagorean theorem, again, because it's a right triangle, and we want to pay attention to which side is the hypotenuse. The hypotenuse is always opposite the right angle, okay? The hypotenuse is the longest side of the triangle, and it is always opposite the right triangle. When you are plugging in a and b, okay, so a squared plus b squared is equal to c squared. It's imperative that we replace c with 15 because 15 is the hypotenuse. However, x and 8, it doesn't matter which one is a and which one is b. It doesn't make any impact at all. So just choose one. This one can be a and this one can be b, or this one can be a and this one can be b. Just make sure the legs are plugged in for a and b, and the hypotenuse is plugged in for c. Okay? So this gives us whatever 15 squared minus 8 squared is. (15 squared minus 8 squared is 161. Then you take the square root of both sides. You do not need to put plus or minus. It is assumed that x is a positive value because it is a side length of a triangle. The exact answer, the kind that question 4 requires, would be square root of 161. So the exact answer is 161. Sorry, the square root of 161. The rounded answer rounded to nearest tenth. We take the square root of 161, put it in the calculator, and it rounds to 12.7. This problem did not include units, so you don't have any units to include. But just pay attention to the directions. If the directions say exact answer, leave it in the square root. If it says round, then round, and make sure that you round to the appropriate decimal place. Okay, question number 5 from MyOpenMath is a word problem requiring the use of the Pythagorean theorem. A 15-inch laptop has a screen that is 7 inches tall. How wide is the screen? All right, so let's draw us a white laptop screen. A laptop screen is a rectangle. That looks a little better. Oh, that's a bad rectangle. All right, there you go. All right, so now the diagonal of the screen is actually what determines this number right here. So when a computer says it has a 15-inch screen or a 10-inch screen or a 20-inch screen, it's referencing the diagonal length of the screen. So that diagonal length is 15 inches. Now, since we have a rectangular screen, of course, we have right angles in every corner. Then we are told that it is 7 inches tall. The screen is 7 inches tall. And then that means we don't know this side right here, right? how wide is the screen. We replace what is unknown with our variable x, and now we can use the Pythagorean theorem. See, we just have a right triangle right here. Here's just a normal right triangle. Of course, if you've ever cut a PB&J in half or a grilled cheese sandwich in half, you know that when you cut a rectangle in half along the diagonal, you end up with two right triangles. And that's what you have right here. So it's pretty simple. You just do a squared plus b squared is equal to c squared. Of course, a and b are arbitrary choices, as in the previous problem, so just pick them. Put them in any order you want right here. You can do 7 squared plus x squared, or x squared plus 7 squared equals to 15 squared. This is 49, so we're going to subtract 49 from both sides. 15 squared is 225. 225 minus 49 is 176. And then we want to take the square root of both sides. Make sure if you take the square root of one side, you also take the square root of the other side in your work. You must show the work to both sides. That's very important. Now, if this problem wants both the exact answer and an approximate answer, which sometimes problems want both, you want to simplify the square root of 176 first into an exact answer, and then you can get a decimal approximation for that answer and match it to the decimal approximation for the square root of 176 as well. And that way you can get both answers and check your work all at the same time. So 176 splits into 4 times what? How many times is 4 going to 176? 44 times. Oh, so that's 16 times 11. So while it is true that 176 breaks into 4 times 44. Notice that 4 is not the greatest perfect square that divides into 176. 16 is. So this number actually simplifies to 4 root 11. And now you can get a decimal approximation of 4 root 11. $13.27. What am I rounding to? In this problem on My Open Math, it says to round to 2 decimal places. So 13.27 inches. And you can also take the square root of 176 and make sure that it's 13.27 inches. Now, if the problem asked me to round, why did I bother to do all this other work? I didn't do it for the sake of this problem. I did it to review with you how to simplify radicals, because it's a worthwhile skill to continue to practice. So I just did this part as additional review on how to simplify a radical. There are 3 main topics that we are addressing right now in this geometric applications. One is the Pythagorean theorem, and we've already looked at that. And the second is how to use reference triangles. These reference triangles I'm going to show you are introduced in high school geometry, but they're essential in trigonometry. So if you're on your way to trigonometry, you'll definitely want to have these in the back of your mind memorized if possible. If not, at least for the sake of getting through this homework, I would recommend that you put them on a 3x5 card and have them handy. A reference triangle is something that you would reference and refer to regularly in order to complete a problem. It's a diagram that you want to use in order to solve your diagram, your problem. You line them up and compare them. Think of it like if you have a model airplane and you have the instructions, and the instructions shows you how to assemble the model airplane, and then you go and put that model airplane together. The reference triangle is sort of the same concept. So let me show you the first reference triangle. It's called the 45-45-90 triangle. The 45-45-90 triangle is a right triangle with congruent legs. When a triangle has congruent legs, it's called an isosceles triangle. A right triangle with congruent legs is very special because it is a 45-45-90 triangle. So what you have are two angles here that are identical. The reason these two are identical are because the base angles of an isosceles triangle are congruent. And they both together add up to 90 degrees. And that equals this angle right here. So the result is you have a triangle that has ratios in a particular, the sides are in ratio. And here is the ratio. You have 1 root 2. Every 45-45-90 triangle in the world, whether it's 300 feet long or 2 centimeters long, regardless of the size, is going to have the same ratio for its side lengths. And so if you have this reference triangle on a 3x5 card or memorized, and you need to figure out an unknown side length of a 45-45-90 triangle, instead of requiring two sides like the Pythagorean theorem does, a 45-45-90 triangle only requires that you know one side of the triangle to solve for the other two unknowns. Let's try some problems. Okay, here's question 6 from My Open Math. Suppose C, the hypotenuse of this right triangle, is equal to 7 square root 2. Find sides A and B, or the values of A and B. That is, they are the side lengths, the legs of the 45-45-90 triangle. Well, the first observation you can make is that a 45-45-90 triangle is always going to be an isosceles triangle. That means that this side and this side, the two legs, are congruent. So once we find A, we have B. Or if we find B, we have A. What we want to do is use the reference triangle. The reference triangle, I'm going to just draw it off here to the side. Remember, has side lengths 1, 1, square root of 2. Now, because both of these triangles are 45-45-90 triangles, they are similar triangles. And in geometry, when two triangles are similar, that means that their side lengths are in ratio. That means you can set up a proportion, okay? So the square root of 2 is to 1, hypotenuse is to leg, as hypotenuse is to leg. You see that? So root 2 is to 1 as C is to B. Of course, what is C equal to? We know that C is equal to 7 square root 2. So now you simply cross multiply. Root 2 times B, 7 root 2 times 1. Divide both sides by root 2. B is equal to 7. You don't actually have to set up a proportion in order to figure this out. Once you get the hang of reference triangles, you can do this kind of work in your head. That's what's used a lot in trigonometry. You do a lot of work in your head. You figure out this trick. If you see a triangle and you know its hypotenuse, and you want to go from the hypotenuse to the leg, you simply divide by the square root of 2. If you have the leg and you want to go from the leg to the hypotenuse, you simply multiply by the square root of 2. So you can use either setting up a proportion. If setting up the proportion makes sense to you, and it's a way that you consistently get a right answer, then I highly recommend that you use this method. If you would prefer to just memorize the ratio between the leg and the hypotenuse and multiply or divide by the square root of 2, if your intuition really latches onto that, you can do it that way too. But I do want you to understand this from a geometrical point of view, not just merely a formula. We have two similar triangles, and we can set up a proportion that represents their sides because the side lengths must be in ratio, being that they are similar triangles. Okay, so let's do another problem, going this time from the side length to the hypotenuse. First, before we do move on to the next problem, I just remembered I didn't find A. So here we go. A is also equal to 7. There we go. Okay, so next problem. Okay, so here is question 7. In question 7, we are told that a leg, is equal to 4, and we're supposed to find B and C. So A and B are of course congruent. So right away we can say that B is also equal to 4. What about C? To go from the leg to the hypotenuse, you can multiply by the square root of 2. So from A to C, you simply multiply the leg by the square root of 2. Now, if you didn't understand why I was able to do that, then it's better to set up the proportion, because ultimately I want you to have a mastery of understanding. So here's the reference triangle. The side lengths are 1, 1, square root of 2. It's good to draw your reference triangle next to your diagram, making sure that you orient the reference triangle in the same way. So both of them have the right triangle down low here. Both of them have the hypotenuse sort of facing up. Just draw them so that it's very easy to make a proportion based off the picture. So the square root of 2 is to 1 as C is to B. Okay, but we don't know C and B. What we do, we can use B is equal to 4. But you could also do it this way. Square root of 2 is to 1 as C is to A, right? You could do it that way too. So square root of 2 is to 1. Square root of 2 is to 1 as C is to A. Replace A with 4. Cross multiply. C is equal to 4 root 2. Now, if you divide by the square root of 2, you will need to rationalize the denominator. Here's a problem that I just made up. I have again supplied the value for C. C is equal to 6, and we need to find A and B. To do that, we can use the reference triangle. You might be asking why I keep erasing the reference triangle if I keep using the same one. If anything, I am demonstrating that when you have a problem like this, it's good to always draw your reference triangle right next to your problem, and just keep doing it again and again, and you'll memorize it through frequent use. Okay, so I have C. I know that root 2 is to 1. Root 2 is to 1 as C is to A. C is equal to 6, so I replace C with 6. And cross multiply. 6 times 1 is 6. A times the square root of 2 is A root 2. Now I divide both sides by root 2. you cannot leave your final answer as 6 divided by the square root of 2. Instead, you would need to rationalize the denominator. To rationalize this denominator, multiply, let me get another color here, green, by square root of 2 over the square root of 2. Remember, you can multiply by a form of 1. If you're only multiplying on one side, you have to multiply by a form of 1. If you multiply to both sides, that's different. But here we already have a by itself, right? This is equal to a. So then we end up with a is equal to 6 square root of 2 over 2, which further simplifies into 3 square root of 2. So it can be a little trickier just depending on the values that are given to you. B is also equal to the to 3 square root of 2. And if a decimal approximation is asked for the problem, you just type that into your calculator. 3 times the square root of 2 is 4.24 roughly. Here I chose to round to 2 decimal places. Okay, so that's how you use the first of the 2 reference triangles. The second of the 2 reference triangles is the 30, 60, 90 triangle. I'll show you that one next. The second special triangle is a triangle whose angles are 30 degrees, 60 degrees, and 90 degrees. This is the other right triangle that is used extensively in trigonometry. The ratios, the length of the sides in ratio are 1 square root of 3 and 2. It's often the case that students have a hard time remembering which number goes with which side. Here's a fact about triangles. The shortest side of a triangle is always opposite the smallest angle. The longest side of a triangle is always opposite the biggest angle. So first of all, you want to know that 2 is the biggest of these numbers. Remember that the square root of 3 is not as big as the square root of 4. 2 is the square root of 4. So we know that 2 is bigger than the square root of 3. And of course, the square root of 3 is bigger than 1. The square root of 3 is 1.7 something, right? You can type it in on your calculator if ever you forget it. It's good to have a decent approximation, 1.73-ish for these radicals. It's good to know those. Okay, so biggest side opposite biggest angle. That's like the Papa Bear. Medium side opposite medium angle, Mama Bear. And littlest side opposite littlest angle, Baby Bear. Papa Bear, Mama Bear, Baby Bear. Okay, now this is the reference triangle, so we can use it for any 30, 60, 90 triangle to solve for any unknown side lengths. Let's try it. Here's question 8 from My Open Math. They've given us a 30, 60, 90 triangle, and they've said suppose B is equal to 8. Then we are to find the missing sides, A and C. Okay, I begin by drawing my reference triangle. Orient your reference triangle the same way the triangle in your problem is oriented. This problem is drawn differently than the way I drew the reference triangle before. So I'm also going to draw the reference triangle over on its side. Smallest angle is opposite the smallest side, so here's the Baby Bear. Medium angle is opposite the medium side, here's the Mama Bear. Biggest angle is opposite the biggest side, here's the Papa Bear. I'm going to add B is equal to 8. I'm going to add 8 to the diagram. And now I can set up a proportion, okay? So 1 is to the square root of 3. 1 is to the square root of 3 as a is to 8, right? As a is to b, replacing b with 8. Another way to say it is baby bear is to mama bear as baby bear is to mama bear. Make sure you keep the rhythm. Baby bear is to mama bear as baby bear is to mama bear. Now I cross multiply. Let me pause and say this. I realized that the problems that I selected on MyOpenMath gave you formulas. So all you have to do is plug in the values into those formulas and get the correct numbers. And that's nice, and I did choose them that way because I want you to get the right answers. But I also really want you to understand this concept. If you are going on to the next math course, College Algebra, and if you especially are going on to trigonometry, you are going to want to understand this concept. So I'm teaching it to you from a conceptual level, from a geometric level of understanding. And I hope that you will understand this. The formula is a backup plan in case you don't. Okay? But understanding the reference triangle and being able to use geometric principles to solve for unknowns in the problem, that is a big accomplishment. So if you're following this, that's awesome, and I hope that it will stick with you and it will make a lot of sense in this course and in the coming courses. Okay, now I have to divide both sides by the square root of 3. Do not cross out your work. If you need to cancel something, use check marks, or if you must, only use a highlighter to cross out your work. 8 divided by the square root of 3 cannot be my final answer for a because we have an irrational denominator. So we multiply by the square root of 3 over the square root of 3. Okay. Very nice. 8 root 3 over 3. Yep, it's that messy and ugly of an answer. The problem may or may not ask you for a decimal approximation. In this particular problem, in question number 8, the answers are likely going to need to be in exact form. I would try it in an exact form first. It doesn't say round. If it doesn't say round, assume that the answer should be exact. Only round if you have a word problem and it's evident that you should be rounding, like to the nearest cent, for instance, if the answer is in dollars, or if the directions explicitly tell you to round. But in general, if the problem does not tell you to round, then don't round. Keep everything in radical form, in its exact form. Okay, what about C? Here's a fun thing to notice. The hypotenuse is 2. The short leg is 1. What does that mean? The hypotenuse is always twice as long as the shortest leg in a 30, 60, 90 triangle, or the shorter leg, since there are technically 2 legs and a hypotenuse. It's a comparative adjective rather than a superlative adjective, right? Okay, so what that means is that if I take the value of A, here's A, and I double it, I get C. So if you can just do this and double it, you'll get the answer for C. Doubling 8, you get 16, so doubling 8 root 3 over 3 is 16 root 3 over 3. You could also set up a proportion, though. Okay, so let's say you have C over 8. You do not know C, but you know 8. That's Papa Bear and Mama Bear. So come over to your reference triangle. Papa Bear over Mama Bear is 2 divided by the square root of 3. And then you can cross multiply, and when you cross multiply that proportion, it will result in 16 root 3 over 3. You will have to rationalize the denominator. It is a lot more work, so it's handy that once you pick up on the relationship between the short leg and the hypotenuse, you can just double. You can just go straight from the short leg to the hypotenuse by doubling the answer, and that's a really handy thing to be able to do. There are other ways you can go easily back and forth between problems. You can multiply the short leg by the square root of 3 and go directly from the short leg to the... Sorry about that. Hold on. I'm sorry for that interruption. I just lost my train of thought. That was my son wanting milk, and he found me. You can never hide from your children in your own house, can you? Okay, so now let's move on to another problem. Question 10 in the MyOpen Math homework, it gives you 2 points. And the question is, what is the distance between these 2 points? I am going to give you 2 different techniques, and you can choose whichever technique you like, whichever one is easier for you to use. I do advise that you try both of them, though, and after trying both, then make the decision as to which technique you like better. All right, so the first technique uses the Pythagorean theorem. And I personally like this technique because then you don't have to memorize the complicated distance formula. So the Pythagorean theorem is a really easy formula to memorize, whereas the distance formula is not. The other reason I like using the Pythagorean theorem to find the distance between 2 points is it gives you more of a conceptual understanding of what you're doing. The more you really understand what you're doing, the more it will stick with you long term, and the less studying you have to do later. So it's a really good strategy for final exams to understand a whole lot more earlier in the course so that you have a whole lot less studying to do later in the course. So what would it look like to solve this problem, that is the distance between these 2 points, using the Pythagorean theorem? Well, first I would need to locate these 2 points in the xy plane. I notice that the first point is in the second quadrant and the second point is in the third quadrant, and you just need to do a really rough sketch of where they're located. I put this point here, -13, 5. It's a rough sketch only. You don't need to put 13 notches, just put a little dot here, roughly at -13, 5. Now for the second point. So here's the second point, -11, -10. I go back -11, or back 11, down 10, and that gives me my second point. So if I connect these 2 dots, if they form a line segment, right? These two points in space, if connected, form a line segment. And the length of that line segment is the distance between those 2 points, right? So if you can find the length of that line segment, then you have the distance between the 2 points. So all you need to do is draw a right triangle. It's a lot easier to draw the right triangle if you are plotting on graph paper. You don't have to plot these on graph paper. You can just do a really little sketch. But the idea is that you should have a leg up and down and a leg side to side, and that the distance between these points ends up being the diagonal, and that diagonal is the hypotenuse. So what we want to do is to ask, what is the horizontal distance between these 2 points? And the horizontal distance between these 2 points is 3. Why? Not 3. 2. 2. Why? Because the distance between -11 and -13 on the number line is 2. These numbers are 2 apart from each other. So we're going to label this side 2. What is the vertical distance? The vertical distance between the right angle here and the point is the same as this distance on the number line, between -10 and 5. Between -10 and 5 is a length of 15. So then we just do 2 squared plus 15 squared. That's a squared plus b squared is equal to c squared. In this case, c, the hypotenuse, ends up being the length of the line segment, which means that c is actually the distance between the 2 points. Now, when I do a problem like this, I'm not going to go through all of the trouble of plotting the points exactly where they are. I will just draw a rough triangle in space. I can just look at the two x coordinates and say, okay, those two numbers are 2 apart from each other, so the horizontal distance between these 2 points is 2. These two numbers are 15 apart from each other, so the vertical distance between these two numbers is 15. And then I can just draw a quick little sketch of a triangle that's 2, 15, and C. So you can get faster and faster at this, but it's good to be able to do it first like this so that you can really understand the concept. So I have a 225 and a 4. So C squared is equal to 229. So C is equal to the square root of 229, and then we're supposed to have a decimal approximation. In this particular problem, the decimal approximation is to 1 decimal place. $15.1. I can hear Bambi really loud in the other room. I hope it's not interfering with math. But at least Bambi is a much better background soundtrack than a whole lot of other movies that could be playing in the background right now. Okay, so there we go. Now, the second way of getting the exact same answer is by using the distance formula. And some people like the distance formula. I tend to steer away from formulas if I can teach a method that's a little more conceptual. But if you want to use the distance formula, you are welcome to do so. So now let me show you how to use the distance formula to get to the same answer. First, you have to know the formula. That's the inconvenient part of the distance formula. Most people retain, I don't know about most people, but a lot of people at least, readily retain the Pythagorean theorem. A squared plus b squared is equal to c squared. Very few people accurately remember, for the long term, the distance formula. The distance formula is derived from using the Pythagorean theorem. They are basically the same formula rewritten 2 different ways. But you see that the distance formula involves a lot of subscripts. We have exponents, we have a big square root, we have complicated things happening under the square root. It's common for students to accidentally turn these minuses into pluses or the plus into a minus. There's a lot of mistakes that can go wrong. But if you are going to use this formula, what I would recommend is that you label the coordinates of the points in the same way that I recommended you label them when you were finding slope, like this. Okay, so now we just plug everything in. And there you go. So you'll notice here that when you have a negative minus a negative, the negative becomes a positive, right? So negative 11 plus 13 simplifies to positive 2. Negative 15 squared, if you are using the distance formula and showing this work, this negative has to be inside parentheses. It's imperative that the negative is inside parentheses before you square it. And you end up with the exact same answer. It's easier to make mistakes with the distance formula, but some people like it, and I have no problem with you using it if you can use it accurately, and especially if you understand what you're doing. So that's pretty much it. We have a shorter lesson in terms of the number of problems, but the concepts are a little more difficult. And so since you only have this one lesson for today, I really urge you to dig into understanding the use of the Pythagorean theorem in the reference triangles, especially the reference triangles, understanding how to set up proportions for similar triangles. These are bigger comprehension problems, and they synthesize multiple areas of mathematics together. And the more you can synthesize different areas of mathematics together, the better equipped you will be to handle more complex problems. All right, I will be posting more information soon about the upcoming tests, so make sure you are paying attention to the announcements on Blackboard. And otherwise, I will see you in the next lecture.